This webinar will discuss how one can do least squares fits in Maple. There are 4 packages that contain a total of 13 Maple commands relevant for least squares calculations. First package is the CurveFitting package. It has a least squares command that fits the data univariate linear models, or models linear in the parameters. The return is a fitting function that can be calculated either exact or numerically. It returns a general solution for underdetermined problems, but does not provide a solution corresponding to the minimum norm parameter vector. The LinearAlgebra package also has a least squares command for univariate models linear in the parameters. This command will obtain either a general or minimum norm least squares solution. It can be given as input set of equations, the only command where you can give it a set of equations, or it can be given matrix vector formalism. There's also a LinearSolve command. It will return a minimum norm solution for underdetermined but consistent equations given in matrix vector form. Does not provide a least square solution for an overdetermined system. The optimization package has 3 relevant commands: nonlinear program solve, minimize, least squares solve. For the NLPSolve command, you obtain a local minimum of the sum of squares. Minimize simply minimizes the sum of squares, but it supports various kinds of constraints and bounds on the variables. And the least squares solve command obtains a local minimum of this sum. GK can be either a residual or some function, so it's a sum of squares of either residuals or functions, and you're obtaining a local minimum. And it also supports various constraints and bounds on the variables. The statistics package has 7 relevant commands. The fit command is a traffic cop. It passes linear models to LinearFit and nonlinear models to NonlinearFit. LinearFit sends linear models to numerical linear algebra tools, and NonlinearFit sends nonlinear models to the least squares solve command in the optimization package. Polynomial, exponential, log, and PowerFits, these are special functions that do exactly what their titles say. You get a polynomial fit, an exponential fit, log fit, PowerFit. The exponential fit is this function, but it's linearized to this form. Log fit is already in a linear form, but PowerFit, which is this function, is linearized. And I'm going to say something about the effect of linearization in a later example. Now, the statistics package is the only package where regression information is generated. And you can get these pieces of information. There's 20 altogether. There's 12 on this side, 8 on this side. For a linear model, you can get all 20 bits of information in this table. For nonlinear fits, you can get these 8. Now, the universe of discourse over which we want to apply these techniques and commands have been subdivided as follows. I think in terms of equations, here we have more equations than unknowns, so there's too many equations. Here you have just enough equations, and here you have too few equations. And in each case, I'm thinking any redundant equations have been removed. So this is the categorization after redundant equations have been removed. Now, if you have too many equations, then necessarily the equations are going to be inconsistent, and that's immediately a call to least squares. If you have exactly the right number of equations as you have unknowns, those equations can be consistent or inconsistent. If they are consistent, then you're just solving equations. I call that interpolation. If they are inconsistent, then you're going to look for a least squares solution. For too few equations, they can be consistent or they can be inconsistent. In either case, you're going to be talking least squares. Now, to illustrate the use of these techniques, I've got a collection of examples. Univariate models, multivariate models. Either you have too many equations or you have too few equations. You have same thing here, too many equations, too few equations. Too many equations, linear, nonlinear. Too few, linear, nonlinear. Too many equations, linear, nonlinear. Too few, linear, nonlinear. In the linear case up here, equations, inconsistent necessarily, inconsistent necessarily. Here, too few equations, could be consistent, could be inconsistent, whether it's linear or nonlinear. Too many equations, linear, nonlinear, necessarily inconsistent. Too few equations, linear, inconsistent, nonlinear, consistent, inconsistent. So let's take a look at example 1, which is univariate linear model where we'll have too many equations which will necessarily be inconsistent. Fitting function is this sum of 5 trig terms and a constant, and for data points we'll take 10 uniformly spaced data points. We'll have them lie in 0 to 3, and the y values will come from y equals x squared. So let's initialize. Here is the fitting function defined as a function. Here is a list of x coordinates equispaced between 0 and 3. And the y values come from y equals x squared. The curve fitting package will provide the LeastSquares command. So we'll apply LeastSquares. You have the separate x values, y values, variable, and the fitting function. The return is the fitting function. You want to see how good a job was done. Here is a graph. You can see the points we've picked along y equals x squared. Fitting function is in red, has wiggle in it as one would expect. There is the curve fitting assistant, which would be able to do this calculation interactively. Assistants live here. Tools, assistants, curve fitting is here. There are, I think, 20 of these tools. Other tools, optimization, graphing tool, differential equation solver. So you have these various interactive tools. If you write a list of the x and y coordinates and then use the context panel to access curve fitting, the interactive curve fitting option provides, I'm going to close that again, provides a dialog that looks like this. Because Maple knows what f of x is, so in the least squares category, you type f of x, it knows what the function is. It draws a graph of the points, the data points, because you clicked on those data points, so it knows what they are, and then draws the fitting function. which happens after you click plot. It also provides the fitting function itself here, and when you're done, you can return the interpolant, which would be this, or the graph, or neither. So that calculation can be done interactively. The LeastSquares command in the linear algebra package can be applied to equations, and here's how I'll form the equations. F is function evaluation. The tilde means apply that element-wise to this list of x coordinates. Equate takes the members of this resulting lists and equates them to the corresponding members of this list, so you get f of x equals y for each of the 10 data points. And this is a sequence of the names of the parameters. The return is this set of equations. Each equation gives you the value of one of the parameters. Now you can cast this problem into a matrix vector form. If you use the generate matrix command, this is again, these are the equations. This is a list of the unknowns. And then apply the LeastSquares command to the sequence. A is the matrix, V is the vector of right-hand sides. You get back a vector of parameter values, and they match the parameter values that you found earlier. The LeastSquares solve command in the optimization package will take as an input a list of vector matrix. And if you just hark back to the linear algebra package, you'll notice this is a sequence matrix vector, but here it's a list vector matrix. But the return is the same vector of parameter values and also the value of the sum of squares. You can also give the LSSolve command a list of residuals. So f of x minus y is the residual, and it will return essentially the same information. Here's the sum of squares, and then a list of equations, each equation giving the value of one of the parameters. Finally, let's see what the statistics package has to offer for a problem like this. Okay, we'll make use of the LinearFit command. Now, raise the info level for statistics to its highest value. So internal remarks get printed, and at the end of this computation, I set it back to its default value, 0. Okay, so the LinearFit command is given list of basis functions, 5 trig functions and a constant, the x and y values and the variable, and you see that the echo produced by this info level raising tells you you're in LinearFit, and then there's this SVD tolerance, which I will have more to say about in a later example. And then you get information like confidence level, sum of squares, the actual model, this is the fitting function, parameter values plus some statistics about the parameter values. You get an R squared and an adjusted R squared value. Alternatively, if you issue the same command with the extra option summarize equals embed, then you get the fitting function, and here it's repeated. You get the coefficients and the information about the coefficients in a slightly neater display, R squared and adjusted R squared, and then you get information about the residuals, information that is part of regression. In this form of the command, we are giving it the fitting function itself, and the information displayed is essentially the same. For regression analysis, use the option output equals solution module. That means that all of the information that Maple has with respect to regression analysis is put into a basket, technical term, module, whose name I'm giving M. One then rummages in the basket by asking for results. You can give individual items and get back information on that individual item. And here what I've done is I applied the print command with a tilde, so that is applied to each item in that basket, and it prints each member of that module on a separate line. It's a little bit easier to read than having it all tangled up in one big mass. And so here is all the information that Maple can provide with respect to regression. And there's one other thing that you can get. You can get this error plot, which is part of statistics. And I've superimposed the graph of the fitting function. So here's the fitting function in red, and the error plot gives you the graph, data points, and these error bars on the data points. Now for our next example, I'm going to skip these special cases where linearization takes place, and I'm going to use example 5 to illustrate a nonlinear fit where you have too many equations. So linear model, nonlinear model, univariate, too many equations, necessarily inconsistent. The fitting function is the Michaelis-Menten model used in many of the biological sciences. This is a set of real data, 46 data points, real data. It came to the statistician at Rose-Hulman in the math department from the bioengineering folks, and the statistician brought it to me and said, how do you do this in Maple? This is real data, something about blood serum levels in a bunch of pigs, something like that. I've used this example in other places. My advanced engineering math book, and I wrote a reporter article on it, and so forth. The solution here proceeds as follows. First, we define the fitting function as a function. Then we write the sum of squares. And there are two linearizations that apply to this problem, linearization 1 and linearization 2, and I carry out the details of that linearization in each of these two columns, the result being that we have two fitting functions that come from two different linearizations, but just compare the results. 1.82, 1.47, 1.92. So these two fitting functions differ, and I'm going to now consider a nonlinear fit, which I can get, for example, from statistics, nonlinear fit. Fitting function, data, variable. What do I want as output? Just two things, the fitting function and the sum of squares of residuals. Notice these numbers, 3.47 compared to 1.820. Down here it's 8. This is 1.419. Great difference in the nonlinear fit. If we use the LeastSquares solve command in optimization and apply that to a list of residuals, we get essentially the same information. The A and B values are pretty close, and the sum of squares, this number is half that. You can see if you double 8, you get 16. You can even use the normal equations, differentiate the sum of squares with respect to the parameters a and b, solve for a and b, and you see that a and b are these two numbers. So the nonlinear fit appears to be corroborated by several different techniques. The sum of squares for the first linearization is 6.4. For the second, it's 4.5. And for the nonlinear fit, it's 1.6. Much better. And here's a graph that visually shows what's happening. These are your data points. In black is the nonlinear fit. The red and green are the linear fits. So I came away from this activity, from this exercise, with a healthy disrespect for linearization. And recently, I remember in the last year or two, remember reading someplace where somebody in the biological sciences was admitting that perhaps the linearization techniques that they had been using with this Michaelis-Menten model were no longer the best thing to be using, that with modern tools they can do a much better job with less work using a nonlinear fit. For our next univariate example, we'll pick a case where we have too few equations in a linear model. We'll begin with a consistent set of examples of data. So the fitting function is this quadratic, 3 parameters, x squared, bx, c. 2 data points. So you'll have 2 equations and 3 unknowns. We'll begin by initializing. So we load the linear algebra package and define the fitting function. Well, this example is essentially solving equations, interpolation I call it. Okay, here are the 2 equations that the 2 data points generate. F of 1 is 5, f of 2 is 3. Solve for 2 of the parameters in terms of a third. So I've solved b and c in terms of a, which gives me as a fitting function this expression that stands for a 1-parameter family of fitting functions. Now, to see how varied that family is, I've got this slider control graph. As I move the slider, I vary the value of the parameter a, and you can see how varied that member of the family is. Quite a lot of flexibility there. Now let's see what happens if we make use of the CurveFitting package. Well, the tool there is LeastSquares command. So here is a vector of x coordinates, and here's a vector of y coordinates, the variable, and the fitting function. The return is an expression that gives a 1-parameter family. Maple uses underscore, and it underscores t because it's created the variable, and it subscripts that variable. That subscript changes as you re-execute this command during the course of a session. That index will change. Now let's apply the tools of the linear algebra package. There's also a LeastSquares command. We can give it equations. So f of 1 is 5, f of 2 is 3. There are 3 parameters. There'll be a free variable. I can name that variable to be s, so I don't get the underscore, but I do get the subscripts. So here is the resulting 1-parameter family of fitting functions. If we convert to a matrix vector formalism, we make use of the generate matrix command. So here are the equations, here are the unknowns, and we get a matrix, I call it A, and a right-hand side vector V. And then we apply the LeastSquares command with AV, and I tell Maple the free variable has name S, and I get back a vector of parameters, ABC. If I include the option optimize equals true, then I get a minimum norm least squares solution. And to verify that, I'm going to project the general solution onto the row space. So the row space command gives me a basis for the row space. They will be row vectors. So I transpose that, make them column vectors, so I can use the projection matrix command to produce a projection matrix which will project onto the row space. So P times V will project this least squares solution onto the row space, and you can see that the projection is the same as the minimum norm solution. So the minimum norm solution is the projection of the general solution onto the row space. And finally, I've added to this slider control graph a graph of the solution corresponding to these parameter values. That's a green parabola. There is a value of the free parameter which makes the family correspond to this minimum norm solution. And I have always wondered, and I don't know the answer to this, what is unique about the minimum norm solution with respect to the problem of curve fitting, least squares curve fitting? Is there some property of the fitting function that's produced when you get the least squares minimum norm solution? I don't know what that connection is, if there is any. So I leave that to any participant to investigate that. And finally, let's consider any other alternatives. Well, there are none. The numeric solvers of the optimization package, being local, will not necessarily find the minimum norm solution, and therefore it can return any member of the general solution. And the same problem exists with the numeric solvers of the statistics package, all of which reject underdetermined problems. So really, there are no other alternatives. For an example of an underdetermined linear system that's inconsistent, let's try example 7. In example 7, I make use of the same fitting function, but now my data points are 1, 5, and 1, 3, so I'm going to end up with inconsistent equations. And I'll initialize by loading linear algebra and then defining the fitting function as f of x. So let's apply the tools of the curve fitting package, which is the LeastSquares command. So LeastSquares, data, variable, fitting function. The return is a 2-parameter family. You see the underscore t, this is a 3, that's a 2, so there's 2 different parameters, 2-parameter family of fitting functions. So I've used a and b for simplicity for the 2 parameters, and I wanted to see how general this family is visually, to see if visually I could make some sense out of how big this family is. And then let's see what the linear algebra package has to say about this calculation. So again, there's a LeastSquares command in linear algebra. You can give it equations. F of 1 is 5, F of 1 is 3. Necessarily consistent. Free parameter name will be S, so that I will get an S2 and an S3 as the free parameters. If we generate a matrix vector form, we have a matrix A and a vector of right-hand sides V. So let's ask for LeastSquares fit. This is the vector of parameter values, and then this is the actual fitting function. The optimize equals true option returns the minimum norm solution. As we just did, I'm going to build a projection matrix, and I'm going to project the general solution onto the row space. So this is the projection matrix. This is the projection of the general solution onto the row space. It agrees with the minimum norm LeastSquares solution. Nonlinear, underdetermined example. Let's begin with a consistent example. So that's number 8. So here is the fitting function that's nonlinear in the parameters, e to the ax here, log c here, 2 data points. So it's going to be an underdetermined system because there are 3 parameters. To get a solution, we first define the function, the fitting function. This is equation solving. We have 2 equations, 3 unknowns. At best, I can solve for 2 in terms of the third. I have managed to do that here with the MapleSolve command, so we have an analytic exact representation of the family, 1 parameter family of fitting functions. And this is only possible if you can get an exact solve, an analytic solve. Otherwise, you can't get values of the parameters as functions of one of the other ones. You can get a LeastSquares approach by obtaining first the sum of squares of residuals, looks like this, and then applying the normal equation. So you differentiate with respect to a, b, and c, get 3 equations and 3 unknowns. Maple returns values, specific values for a, b, and c. So you have gotten 1 member of this 1 parameter family of fitting functions, and you get 1 solution here because we've used FSolve, which is a numeric solver. And so over here we have a slider controlled on the member of the family, that's in red. The green curve is this 1 curve here, and I'm left with the same question that I had earlier. What is the connection between this 1 solution, if there is any connection, and the actual problem, the mechanics or the concept behind this fitting? What is the mechanistic connection between that solution, which is 1 member of this family, and the family itself? Underdetermined, univariate, nonlinear, inconsistent. That's example 9. So I use the same fitting function that we just used in example 8. And we take our 2 data points as 1, 3, and 1, 5, so the equations are going to be necessarily inconsistent. So we define the function. We form the sum of squares of residuals. Make use of the normal equation, so you differentiate with respect to a, b, and c. You get 3 equations and 3 unknowns. And if solve can obtain one of the parameters in terms of the other 2, then you can form a 2-parameter family of fitting functions. This is the value of the sum of squares for all these members of this 1 parameter family, 2 two-parameter family. If you work numerically, you approach this as a least squares problem, you differentiate with respect to A, B, and C, and you solve numerically. You get specific values of A, B, and C, which gives you a specific fixed fitting function. And as we did earlier, I've looked at the family. Now this has two sliders. If my hand would hold steady, clearly there's a value of A and B that show this single solution is indeed a member of the family. What is the connection? Now let's move to some multivariate examples. So we begin with the case of overdetermined. We have too many equations. We'll do a linear model, necessarily inconsistent. This is example I call 10. Fitting function. A, B, C are the parameters. Basis functions are sine x, sine y, cos x, cos y, sine x, cos y. And I'm going to have 9 data points, which will be the node values in 1, 2, 3, direct product 1, 2, 3. So to generate some data, what I did was I said, take the model to have values for A, B, and C, 3, 4, 5. This is the column of values that I would compute using this function little f at those nodes. Then A is the matrix containing the x and y coordinate values, and V is the vector where I've taken these numbers and rounded them off to integer values. So my problem is contained in the data A, V. So statistics, LinearFit, because this is a linear model, you give the basis functions. There are 3 of them. Then the data, then the variables. And one returns a fitting function. This is not 3, this is not 4, this is not 5, but it's close enough. Visually, to see how close, I have graphed the 3, 4, 5 function in green and the fitting function phi in red. That's not too bad. Now let's use the LeastSquares command in linear algebra. So the general fitting function, I use a uppercase F, ABC. That generates equations, because here I am evaluating this function. These are the x coordinates, these are the y coordinates, and these are the function values, the observed function values. So I make a matrix. So this is the matrix. I call it C, and U is this vector which was V up above, the vector of function observed function values. Linear algebra's LeastSquares command returns this vector of parameter values, and that seems to agree. I can go back to that. Let's go a little ways up. If you look at these numbers, 2838 and 55, 2838 and 55, 2838 and 55. Okay. To take these values and get them into the fitting function, we use the equate trick. So ABC are the names, P is this vector. Equate sets A equal to the first component of P, B equal to the second component, C equal to the third component. So I get equations which eval command requires. And so I'm making substitutions into the fitting function. And I get back the fitting function, which I compare to the one I got earlier, phi, and you see these are the same, essentially the same functions. Multivariate case, overdetermined, nonlinear, necessarily inconsistent. I will use this example 11 with this nonlinear fitting function. I've put in place the linear algebra package. This is the fitting function. I need data. So this matrix contains in the first column x coordinates, second column y coordinates, and these are observed values. This matrix has full rank, so this will indeed be an overdetermined problem. By way of solution, begin with an initialization step, define the function, and form the sum of squares of residuals. So here is the function evaluated at an x-y pair. This is the observed value. That difference is squared, summed. The tools of the statistics package include NonlinearFit, because this is a nonlinear model. There is the fitting function, matrix containing the data, variables, and I will simply have this command return the fitting function and the residual sum of squares. That puts the residual sum of squares second, and here are the values of a, b, and c, fitting function. Now this graph shows as dots the data points, and the surface is the fitting function we've just calculated. In the optimization package, there is the LeastSquares solve command. This is a sequence of residuals in square brackets, make it a list, function evaluated at x and y minus the observed value. What is returned here in a list of equations for the parameter values a, b, and c, and this is half the sum of squares. Compare that to that. It's half the sum of squares, and look at these numbers: 1, 2, 8, 8, 8, 1, 2, 3, and 3, 8, 3, 6. So those two agree. Here I've doubled this sum of squares here, and to see that it's the same as what we got earlier. If you use the minimize command, optimization package, you're minimizing the sum of squares. It's a local calculation, but in this instance it returned the same solution essentially that we got here from LeastSquares solve, except here you get the full value of the sum of squares, whereas here you get half the value. Multivariate case, underdetermined, a linear model that will be inconsistent. Example 12. I've loaded the linear algebra package. I have a matrix of data and a vector of observed value. The fitting function has 4 parameters. It's linear in structure. These functions x, y, and z can be arbitrary functions of x, y, z. I've taken the simplest case of choosing x, y, and z. The fitting function will be called phi. This matrix A has rank 3, so there will only be 3 equations, and they will be inconsistent, and the system is underdetermined. By way of solution, let's look at what we can find with the tools of the linear algebra package. So augment A with V and row reduce to reduced row echelon form. This bottom row is the equation 0 equals 1, so inconsistent, but rank 3, so there are 3 equations, 4 unknowns, but the whole set of equations is inconsistent. LeastSquares command. Data, free variable will be called S because it has to be one free variable. Maple uses the subscript 4. This is the minimum norm solution, and here it is floated in floating point form. Now this is the general solution. I'm going to build a projection matrix P, project onto the row space. I'm going to project that general solution onto the row space, and I get the minimum norm solution back again, and I floated it, and it agrees with what we already have. Now, if you apply LeastSquares command to a completely floating point version of the problem, so I floated A and floated V, you get back a numeric solution, which in this instance happens to be the minimum norm solution. Now, why Maple computes the minimum norm solution? You would have to look in the code for this command to see what actually it's computing, but you would expect to get back at least one member. The fact that that one member of the one parameter family of fitting functions is the minimum norm solution takes me by surprise. Now let's see what the tools of the statistics package can do. So we use the LinearFit command because this is a linear model. We give the basis functions 1x, y, z, float A, float V, and these are the variables, the unknowns. Now, the command detects that this is not a full rank matrix A, but it does return the fitting function that we just found up here. It is the minimum norm solution. Now, it's time to explain this SVD tolerance parameter. Maple has two ways of going about one of these computations. It computes SVD, singular value decomposition, or it computes QR, decomposition. QR is less expensive to obtain, and Maple tends to try to use that whenever possible. But there's a switch that tells Maple the problem is too ill conditioned to continue using QR. You've got to use SVD. That switch is this SVD tolerance. So Maple computes the singular values and then uses the singular values as a way to estimate the condition number. Now, the singular values come out largest to smallest. So this is the smallest singular value divided by the largest. So this is an estimate of the condition number, but it's reciprocal. So it's the reciprocal estimated condition number. And it turns out in this problem, this is its size. It's smaller than the threshold value, 10 to the minus 12. Therefore, Maple kicks over from QR to SVD. So if you raise info level and you run LinearFit, you see here the tolerance level, and you see that all the information we showed earlier for regression. This is the fitting function is up in here. The R squared is here, repeats the fitting function. If you invoke the LinearFit command with an SVD tolerance that's smaller than what you actually have, then maybe we'll continue using QR. And when it uses QR, it produces this fitting function. Now look at these numbers. 10 to the 14, 10 to the 14, 10 to the 12. It's producing gibberish. So the SVD tolerance is a useful parameter switch for problems in which you want to make sure that the calculation uses SVD rather than QR. Multivariate case, underdetermined, nonlinear. Let's take an example in which the equations that result are consistent. Here's a fitting function, 3 parameters, nonlinear. I've loaded the LinearAlgebra package. I need some data, so here is the data, x, y, and observed value. By way of solution, we define the fitting function, and we form the 2 equations that correspond to this data. This is the function evaluated at the first data point equal first observed value. This is the second. So we have 2 equations in 3 unknowns. I'll apply the solve command looking to obtain values of 2 of the parameters in terms of the third. And I can do that here. B and C are given in terms of A, which means that I can form a 1-parameter family of fitting functions. This is the 1-parameter family of fitting functions. Let's see how varied that solution surface is. We use a slider, run through some values of A, and you can see what happens to that fitting function. Now, if you go to optimization, you're going to work numerically. This is the sum of squares. So this is one residual squared, and this is the other residual squared. Minimize returns a list of 3 equations, A equals B equals C equals. So you have the values of A, B, and C, and here you have sum of squares. So placing these values into the fitting function, we have 1 member of that family of fitting functions. And again, let's see by means of this slider if that 1 member is really in this family, and it appears to be. And so we again have that question. If you do a computation numerically and you get 1 solution, but you don't have your hands on a representation of the whole family, what can you say about that 1 member? What are its characteristics that would let you go ahead and use it in the application from which it came? And finally, multivariate example, underdetermined, nonlinear, and now we'll have the equations be inconsistent. And that's our example 14. We'll use the same fitting function that we use in example 13. Difference is we'll make sure that the equations that result are inconsistent. So the x and y coordinates are the same, but the observed values are different. And that will make the equations inconsistent. So again, we defined a function. Here are the 2 points, x, y, and observed, x, y, and observed. So this becomes a residual squared plus a residual squared. So this is the sum of squares of the residuals. If the solve command applied to the normal equations, differentiated with respect to a, b, and c on the sum of squares, if I can solve for 1 of the parameters in terms of the other 2, I can end up with a 2-parameter family of fitting functions. It all depends on the strength of that solve command. If you are forced to work numerically, then you cannot get this family. You will only get one member of the family. So here I've got that visual for that 2-parameter family of fitting functions. How varied is that family? We'll get some idea how varied that family is. If you make use of the minimize command in the optimization package, you're working numerically, you will get one solution, A, B, C, one set of values. This is, I believe it's half the sum of squares. This then becomes that one member of the fitting function family. And here again I've added this one member to the slider control graph to see if we can verify somehow that this is a member of the family. And you see that A, I've used A and B. A should be around 0.8. Let's see if we get that to be around 0.8, something like that. And B, 0.9, a little bit more. See, it's close. We did it. Okay, so this is one member of the general family. If you are forced to work numerically because you cannot solve these equations exactly, then you will get one member of the family. You will not have any idea of the extent of that family. You will be solving a problem. You will have one possible solution to that problem. You will not know the full gamut of possibilities of solution to that problem. What is the connection? I think that's something that should be investigated.